Hello and welcome to the solutions video for the Physics 20 Unit 2 Makeup exam. Let me just reposition my windows to make sure everything is coming through. And here we go. So the physical quantities that are vectors here are velocity, displacement, and acceleration. Time, distance, and speed are not. Distance is the scalar version of displacement, speed is the scalar version of velocity, and time has no real direction, at least not in our perception of space. Now we want to convert this vector, 4.9 units 31 degrees west of south, into components. So let's take a look at where this is. We could do it, we can do it with either Desmos or a whiteboard. Let's actually use a generic whiteboard for this one. So here are our axes. And our vector is 31 degrees west of south. So let's grab our vector. We start going south, we swing it up 31 degrees. So with that, the angle in standard position is 270 degrees minus 31 degrees. Because this 31 degrees west of south goes here. So that is 239 degrees, and our magnitude is 4.9. So the x component is 4.9 times the cos of 239, and the y component is 4.9 times the sine of 239. So writing those through the calculator, our x component to two significant digits is a negative 2.5, and our y component to two significant digits is a negative 4.2. We use the two sig digs from the 4.9. Now, a motorcycle travels 80 meters north in 15 seconds, and then turns around and goes 60 meters south in 10 seconds. Distance does not care about direction. 80 plus 60 is 140 meters, not 140 north, just straight up 140. The displacement is the 80 north minus the 20 south for 20 meters north, because their direction does matter. The average velocity is 20 divided by 25 to give us 0.8 meters per second north. Sorry. This doesn't ask for speed. If it did, it would be the 140 divided by the 20 seconds. Or 25 seconds, sorry. So that would be around a 5.6 or so. Now, a vacationer on her newly purchased sailboat moves at a constant velocity of 8.9 meters per second south for 38 minutes, and then returns north at a speed of 3.7 meters per second for 48 minutes. The magnitude of the total displacement of the vacationer for this trip is. So we need to figure out how far this vacationer goes. So we start with 8.9 meters per second south for 38 minutes. So 8.9 meters per second. It's southbound, so we're going to make it negative. And we multiply it. Actually, no, hang on. Sorry, it's not asking for hours. So it's not 38 divided by 60 to turn them into hours. It's 38 times 60 for seconds. So this first displacement is a negative 8.9 times 38 times 60. That's at negative 20290, and that'll be meters. Now I know in class I would often plug in the TI and show the display. I don't have that at home where I'm recording this one. I don't have the TI calculator at home at all. I do have the Calculate 84 app for my phone, which is a free emulator for the TI-84. And our other distance here is now 3.7 meters per second for 48 minutes. So that's a positive 3.7 meters per second, 48 minutes times 60 seconds. That's 10656 meters. All right, and when we add these up, it's a negative 9636 meters. So this vacationer has gone almost 10 kilometers south. And here we just have the magnitude, so we don't have to worry about the negative. Right, the question is just asking for the magnitude of the total displacement. And it's asking in kilometers. So this rounds to 9.64. Now, an Olympic speed skater accelerates to a speed of 14 meters per second over the first 10 meters of the race. The magnitude of her acceleration is. So, speed skaters typically start from rest if they are not cheating. We don't have time. So given our two velocities and no time, what we want is Vf squared equals Vi squared plus 2AD. We are asked for acceleration. So that's Vf squared minus Vi squared over 2D. So that is 14 meters per second. Squared minus it's exactly 0 meters per second, and it is a 10.0 meters. So everything we've been provided has been provided to 3 significant digits. So 14 squared divided by 20. The acceleration comes out to 9.8. And again, everything we're given is given to 3 significant digits. You throw a pebble upward and it reaches a maximum height of 6.40 meters above where it was thrown. The speed of the pebble as it leaves your hand is. So again, we have the height. We can assume we're on Earth, so we know the acceleration. The final velocity, when it reaches that maximum height, is 0. We're asked for the initial velocity. So we're going to use the same equation we just used. It is Vf squared equals Vi squared plus 2AD. So our Vi, algebraically, we are going to have either the positive or negative square root. Physically, we are looking for this, or we know in this situation it starts off upward. So we can manually select that it's the positive root. If we had the peak and we're looking at it as it fell, then we go for the negative. So we know it's coming to a stop at the peak. The acceleration due to gravity is a negative 9.81 meters per second squared. And the distance is 6.40 meters. So the negative will cancel here. Works out to roughly 11.205712887 meters per second, or 11.2 to our 3 significant digits. Apologize for the coughing we have here. Now, after stepping out of his hut for some fresh rainforest air, Timmy encounters a velociraptor. Timmy is 17.7 meters away from the door of his hut when he spots the velociraptor 38.9 meters from his own position, as illustrated below. If this diagram is to scale, this is clearly a movie velociraptor, considering the real velociraptors were more like large chickens, small turkeys in size. If the velociraptor can run at a constant speed of 14.8 meters per second, Timmy will need to run a speed of how many meters per second to make it back to the safety of his hut? Here we assume that Timmy just needs to reach the door just as the velociraptor would. So, how fast can the velociraptor make it? We look at the total distance and divide it by the speed. So the velociraptor is going to make it in 38.9 plus 17.7, all divided by 14.8 meters per second. So the velociraptor makes it there in 3.82 seconds. Timmy has to go 17.7 meters in exactly that much time. So Timmy has to go at about 4.63 meters per second. And if the velociraptor starts at rest and accelerates at a constant rate of 6.4 meters per second, well, we are changing the conditions here. Same total distance, the 38.9 plus 17.7. But now we need to figure out how much time it takes the velociraptor to get there, given we have the initial speed and the acceleration. So this is not just a straight v equals d over t. So here I'm going to go back to our whiteboard. Our d is vi t plus 1/2 at squared when the velociraptor is starting from rest. So we manipulate the algebra. We get the time is 2d over a. That distance is still that 38.9 plus 17.7. And our acceleration was 6.40 meters per second squared. So 2 times 38.9 plus 17.7 divided by 6.40. Take the square root of that answer, and the velociraptor is going to take a little bit longer to get there this time. And Timmy is again moving at a constant speed, so we take that 17.7 and divide it by this answer, and he needs to go about 4.21 meters per second to escape this time. It could be a little bit slower because it takes the velociraptor a little bit longer to get there. All right, a river excuse me, that is 300 meters wide has a current of 15 meters per second north. The boat leaves the west bank of the river and travels at 4.4 meters per second at an angle so it lands straight across the river on the east bank. All right, let's draw a picture of this. So, these are the banks of the river, and the current is flowing north. So our boat pushes itself. Oh, I drew that facing the wrong way. We have to balance for a southern or a northerly current, so the boat has to go a little bit south to end up traveling straight east. So it's got to head into the current a little bit to offset it. We need to figure out the exact value. So we know that the boat moves at 4.4 meters per second, and the current is a 15.5 meters per second, or 1.5 I should say. So to find this angle, we want the inverse sine. This is an opposite over adjacent problem. So that angle is about 19.93, etc., degrees. So here, if we round it to the nearest degree, it's 20. And that direction C is going to be 20 degrees south of east. That's how we have this drawn. So that's 2. And how long will it take for the boat to cross the river? Well, for that we need the horizontal component. So that's 4.4 times the cosine of our answer. We could also do it by taking the Pythagorean theorem, 4.4 squared minus 1.5 squared. The calculator agrees that it's 4.136423576 meters per second in that easterly direction. And a river is 300 meters wide. So 300 divided by that answer is 72. And actually, well, it should round to 73 because we only have 2 significant digits here. So, going on to number 11. A toy car moves forward off the edge of a horizontal table of a height of 1.2 meters and lands on the floor a horizontal distance of 1.96 meters from the edge of the table. What's the speed of the car as it hits the edge? So for this, we have to connect things through time. Excuse me. All right. So we know the height. We're going to have to use the height to figure out how long it takes this car to fall. So we have our 1.2 meters. That's the height of the table. That's equal to 1/2 AT squared. The time is the square root of 2 times 1.2 divided by 9.81. So it is identical algebra to this problem. We are just changing the numbers. So with this, it is a 0. Oh, hang on. That's just the time. We need the speed of the car as it reaches the edge of the table. So it went 1.96 meters in that much time. That gives us a speed of 3.96. And looking back here, I realized there we rounded to the wrong number of significant digits. It was only supposed to be 2. Sorry, I just checked the answer key to make sure everything was going the way it should be, and it wasn't. So we messed up those sig digs. Number 12, a shot putter launches a shot at a speed of 12 meters per second and an angle of 36 degrees above the horizontal. When it hits the ground, the shot will have traveled a distance of how many meters from where it was thrown? Okay. So we have ground level. And we have a golf ball that goes up and down in a parabola that's a lot more perfect than what I just graphed. So the shot putter launches the shot at a speed of 12.0 meters per second at an angle of 36 degrees. So what we need to do is figure out how much time it takes in the air. And for that, we use half the time. How much time does it take this to reach that halfway point. So vertically, VIY, our initial speed is 12.0 meters per second times the sine of 36 degrees. So 12 times the sine of 36 is 7.05342330. So that's how many meters per second we have. And now we need to figure out how much time it spends in the air. For that, actually, yeah, if we just need the total time, we don't need the peak, no one's asking for the height, then we can just say acceleration is Vf minus Vi over t. So the time is the final velocity minus the initial over the acceleration. So the final will be a negative 7.0534 in the absence of air resistance. When it comes down to the same height it left from, it's moving at exactly the same speed. So the initial is that number but positive. Downwards it's negative. So we can really multiply our previous answer by 2 and divide it by that negative 9.81 meters per second squared. And the time it spends in the air is 1.43800673334 seconds. If this is how much time it spends traveling at our horizontal initial velocity, 12.0 meters per second times the cosine of 36 degrees, we multiply all of these numbers together. And this should give us the answer. At least if I don't make typos as I'm entering things into the calculator. Yes, so this gives us a 14.0. So now we have something that is similar to what we'd be doing in the labs. So for this one, we are measuring the acceleration due to gravity after dropping something from a specific height. So to find our slope, the linearized version of the graph, we take d is VIT plus 1/2 AT squared. Now our initial velocity is 0. So our d is 1/2 AT squared. We are looking for acceleration. So we want that to be our slope. So when we do y equals mx plus b, d is our y value. That's the thing that's isolated on its own. That's going to go on our y-axis, or the vertical axis. Our slope, we're going to want to be our acceleration due to gravity on this planet. Our horizontal position is everything left over in this term once we pull the acceleration out. So that's 1/2 t squared. And ideally, our y-intercept is 0. So we are going to edit our lists on our calculator. List 1 is where our x's go. That'll be t squared over 2. We can actually type those numbers in. So if I enter 1.51 squared divided by 2, the calculator gives me 1.14 and so on and so forth. I continue to do this for the other data points. So I have about 1.14, 2.42, 3.69, 4.74, and 6.02. It's longer than that, but those are all the digits that show up in the app. And our y component is identical to what we see here. the 14, 28, 42, 56, and 70. So we're graphing, it's always y versus x, so it's d versus t squared over 2. Once we have these entered in our calculator, we do our calc. Linear regression is option 4 on our menu, where the x is list 1 and the y is list 2. And when we do this, our slope works out to 11.6 or 11.572, etc. And this solves our makeup test.